Hey everybody, in Honors Pre-Calc. Today we are going to be talking about lesson 5.3, inverse trig functions. And on your screen now, you will see the lesson overview. Our essential question today is, how are the graphs of inverse trig functions similar and different to the original trig functions? And for this, I need you to remember that inverse trig functions are different from reciprocal trig functions. So reciprocal trig functions are when we take sine and we switch to 1 over sine. And that's also called cosecant, right? So sine, cosine, and tangent have reciprocals that are cosecant, secant, and cotangent, respectively. But the inverse trig functions are different. That's when we actually switch the position of x and y in the function. We'll talk about that more today. But we represent that, as you see over here, kind of, if you ignore this tangent, in the what you will be able to do box of this chart. The arc cosine is another way of saying inverse cosine. So there's different notation. You can either write cosine to the -1 or arc cosine. Either way, that's different from 1 over cosine. And the graphs are different too. So we'll take a look at those today. Hey, don't worry. I know we already looked at 6 different trig graphs and their transformations. For inverse trig graphs, we are not going to be looking at any transformations. We're done with transformations, okay? So now we just have to look at the graph to be able to figure out what is going on here. Here is what we're going to do. Students will use composition of trig functions to evaluate expressions. Composition of functions, meaning like a function of another function, like this one that you see down here, tangent of arc cosine. Students will use inverse trig functions to solve for angle measures, and students will graph inverse trig functions over the appropriate domain. What you will already know, about trig functions. You know what a function is. Remember the vertical line test. A function has to pass the vertical line test. And we know what an inverse is. So we're going to combine those things to start to graph these trig functions. So I'm going to switch over to actually Desmos for us to get started. All right, so on your screen now, you see Desmos, and the only function that's graphed right now is y equals sine x. We should know this function like the back of our hand at this point, right? We know that it has a period from 0 to 2 pi. We know it has a maximum and a minimum y value of 1 and -1, and the amplitude is 1. There's more things we know, but that's the gist. And we also know that in order to find the inverse of something, we switch all the x and the y values. So every value that was an x value becomes a y value. Every value that was a y value becomes an x value. All the order pairs switch. So if pi comma 0 right there is a point on our graph, that means 0 comma pi should be a point on our inverse. In other words, what we have to do is flip this function or reflect it over the line y equals x, right? And so I have x equals sine of y, which is just the original with the x and the y switched, which I'm going to graph next. And you can see that the whole thing flipped vertically, right? So pi comma 0 became 0 comma pi, 2 pi comma 0 became 0 comma 2 pi. And instead of having a period that goes horizontally, it's a period that somehow goes vertically. All right, so I'm going to remove the original and I'm going to remove the dotted line so we can just look at this inverse. And I want you to think about this for a second. This lesson is called inverse trig functions. And I already reminded you that a function means that in order for something to be a function, it has to pass the vertical line test. Well, I'm pretty sure that this does not pass the vertical line test. In fact, if I draw a vertical line, say at like, I don't know, 1/2, right around here, what you're going to find is that it actually has infinite points on this curve that intersect with it, right? Because this keeps going on and on and on forever. So we want this to be able to be a function. So what we're going to do is we're going to pick convenient bounds to the range so that we have one complete, and what we're calling it is a branch, one branch of this inverse thing right now, this inverse relation that we want to be a function. So what I'm going to show you now is just what the math lords decided is going to be the most common part of this graph that we're going to want to use. So when I reveal this, you can see that we're actually only going to be interested in this specific branch of the overall inverse sine. And that is because if you take a look, now this passes the vertical line test, right? This purple curve right here only has one y value for every x value. It also still extends as far as it can before repeating itself. So it's going to go from -1 to 1. Let's see if yeah, you can see. Let me get rid of that for a second. So this is the whole graph that we're going to be looking at. Let me zoom in. So it goes up to 1 comma pi over 2, 0, 0, -1 comma -pi over 2. That's the whole graph that we are going to be using, okay? So let me switch over to the notes then, and we will come back here to do cosine and tangent after we do a little bit more of an investigation. All right, so here are our notes, and you can see for the inverse sine function, there's really two different ways we can write it. We can write sine to the -1 or arc sine. Both of those notations mean the same thing. Down here, you'll just see this is just with x and y switched. That's not a way that you would write the inverse sine function. That just indicates that you might be wanting to use the inverse sine function, but we'll get to that later. What I also want to look at is the graphic organizer that goes along with this lesson. If you haven't opened that up or printed that out, or you don't have that in front of you, please get it, or be willing to draw the important parts on your own paper if necessary. But here is the top portion of the graphic organizer, which is all about sine inverse. You can see it's split into thirds. So we have sine inverse at the top, cosine inverse in the middle, tangent inverse at the bottom. So we're going to be starting by looking at sine inverse. And this is going to help us to see how this graph relates to the unit circle. So if you think about like all of the inputs and the outputs switched, it makes a lot of sense what's going to be going on here. So I recommend that you highlight or underline in different colors the same way that I did. The domain of sine inverse is from -1 to 1. We can see that right here on the graph. And where that comes from on the unit circle, because of the branch of that larger inverse sine that we selected, that the math lords selected, we are interested in the right half of the unit circle. Since sine is the y values, that is now our domain. So I recommend that you highlight or underline all of the y values on the right half of the circle. The range then is the angle. So normally with sine, if I told you to find the sine of pi over 6, you would look for pi over 6, and the output would be the y value. Now it's switching. So the 1/2 is the input, the pi over 6 is the output. So if I told you to find the sine inverse of 1/2, you would look for 1/2, and then the angle would be the answer, pi over 6, all right? And you can see that the range goes from -pi over 2 to pi over 2. That's a little different from the angles that we usually see on the unit circle. So I went ahead and drew in here the -pi over 6, -pi over 4, -pi over 3, -pi over 2, and then highlighted those. You will never have to like from scratch redo all of this, but typically I would ask students to, have this memorized. You always have access to your graphing calculator, so you can take a look at this graph. But you will need to know that sine is the right half of the circle. The angles go from -pi over 2 to pi over 2. Okay. So yeah, it's just kind of the opposite of sine. So instead of starting with the angle and the output is the y value, now we start with the y value and get the angle. So let's look at that in action in example 1. Let's find the arc sine of -1/2. So I come over here, -1/2 is the y value I'm looking for. I see it right there. So my answer is going to be the angle -pi over 6. And that also can be seen on the actual graph over here. I'm plugged in -1/2, which is the x value right around there. Right here, this y value would be -pi over 6. I don't actually have all of those marked on here because it would be rather cluttered. But that, just like any function, you plug in the x value, you get the y value of the ordered pair, okay? Let's try letter B, the arc sine or sine inverse of root 3 over 2. So we're looking for the y value of root 3 over 2, and the answer would be pi over 3, the angle right there. Letter C, the sine inverse of 2. And I can tell you right now, I don't see a 2 as a y value for any of these. And I look over here on the graph, 2 would be all the way over here. And there's definitely no y value that corresponds to that x value 2. 2 is not part of the domain. So I'm just going to write DNE, which stands for does not exist. And the reason being because the domain is actually only from -1 to 1, which we could write if we wanted to get fancy in interval notation. And 2 is not in that interval, so doesn't work. All right. So next up, we're going to talk about arc cosine and arc tangent. So I'm going to return us to Desmos so we can examine those graphs. Then we'll look at the graphic organizers, and then we'll evaluate these. All right, let's take a look at cosine. Here's our initial cosine graph. It starts at 0, 1, goes down and gets back up by the time we get to an x value of 2 pi. We know this graph very well. So just like we did with sine, I'm going to plot y equals x, and we are going to plot a symmetrical graph of what we see here over about this line. We're going to reflect over that line, and we're going to end up with this. If you tilt your head and you look so that this dotted line becomes vertical, you'll see that the green and the red are completely symmetrical now across that line. They're completely reflected. Okay, so that proves that this really is, the inverse of cosine. But once again, it is not a function, right? It doesn't pass the vertical line test. So we once again need to pick a convenient branch of this graph to become the inverse cosine function. This time, if we picked, the same as before, from a y value of -pi/2 to pi/2, we would not have the whole graph. It would only be this portion over here. So this time, we are still going to go from -1 to 1 along the x-axis, but we're going to go from 0 to pi along the y-axis. That's one branch. It passes the vertical line test. It accounts for all x values. So I'm going to remove the full thing so we can just take a closer look at that. And you can see that it goes from -1 comma pi to 0 comma pi/2, and then all the way down here to 1 comma 0. Okay, we'll take a closer look at that in a second on the graphic organizer, but let's switch over and examine tangent as well. All right, so here's what tangent looks like. This one's a little weird, right? Because when we reflect this, it's going to look bonkers. So let me show you y equals x. And then here is x equals tangent y. We're going to reflect over that y equals x line. Everything that had vertical asymptotes is now going to have horizontal asymptotes. If you slant your head again and look so that dotted line is vertical, you'll see that you can tell that it's reflected. I'm going to turn everything off though, except for the green, because it's really hard to tell what's going on there. So again, all of our vertical asymptotes became horizontal asymptotes here. And once again, we don't pass the vertical line test. So now we want to pick just one convenient portion or one branch, and we're going to pick the one centered here. And so you can see when I plot this, we're only looking at the central curve of what was that inverse tangent. Okay, and now this is the inverse tangent function. And let's take a look at the graphic organizer then, so we can see where the unit circle corresponds to these graphs. All right, so here is cosine inverse. We have the same domain as with sine, it goes from -1 to 1. The range, though, goes from 0 to pi, like we saw on the graph. Here is that graph again. And once again, I'm highlighting all of the domain in green, and I recommend that you do the same. Since domain is x values, we're going to highlight the x values on the unit circle. And those x values are going to be when the angle goes from 0 to pi, since that's our range. So I'm going to highlight all of those x values in green. The range this time is actually the angles that are on the unit circle from 0 to pi. And that all plotted together will form this curve. If we plot the green as the x values and the pink as the y values on this graph, all of those points will be on that curve. All right. For tangent then, tangent has a domain of -infinity to infinity, which is crazy, but yeah, you can tell when we switched that curve sideways, it just extends forever in both directions. The range, however, now goes from -pi/2 to pi/2. So since that range is -pi/2 to pi/2, when we go over to the unit circle, we have to do the same thing we did with the sine when we write in the angles to be negative. So we have -pi/6, -pi/4, -pi/3, and -pi/2. And what we also need to do is think about that tangent isn't just the x value or the y value from the ordered pair. It's y divided by x. So I went in and wrote in all of the tangent values here, the y's divided by the x's, for convenience. So, well, at the very top, we did 1 divided by 0, which does not exist. That corresponds to the actual horizontal asymptote. So there is no x value that has a y value of pi/2 because that is the horizontal asymptote right there. So it does not exist. Over here, and that's why we have less than and not less than or equal to. This one, √3 divided by 1 is √3, and then 1. This is √3 over 3. Then we have 0, negative √3 over 3, -1, negative √3, and once again, the horizontal asymptote down here does not exist as a point on the graph. So we have some helpful points here. And again, we are going to be plugging in the number on the outside to get the angle as the output in this function. So let's try example 2 from the notes. Find the exact value of each in radians. The arc cosine of √2 over 2. So we're going to look at the cosine unit circle. √2 over 2 is right there. And the output would be the angle pi over 4. Cosine inverse of -1. So we take a look at the cosine unit circle. We look for -1 on the outside, and the angle of the output would be pi. Then we are switching to tangent. So arc tan of 0. Let's see what we got here. 0 is right here. 0 divided by 1 was 0. The output, the angle is 0. That's this point right here at the center of the graph. And the arctan of -1. Here's -1. The output would be -pi/4. -1, -pi/4 is this point right here. Okay. All right. So that is the evaluating of cosine inverse and tangent inverse. Let's keep going with these notes. On the back, we have calculators and inverse trig functions. Use a calculator to approximate the values of each, if possible, round to 4 decimal places. Now, the reason we want to do this is because there's some helpful points that we know of from the unit circle, but there's all sorts of other points on these graphs that we don't have memorized, we don't have on our unit circle, but we can still approximate them with the graphing calculator. So let's take a look real quick. On the typical TI graphing calculators, if you press second sine, second cosine, or second tangent, that's how you get to the inverse. So for this first one, I'm going to do second tangent. Remember, tangent to the -1 and arctan are different notations for the same thing. I am in radian mode, which is good news. That's what I want to be in. And I'm going to type in -8.45. And I'm going to round to 4 decimal places. I could do second sine of 0.2447. So for this second one, I get 0.2472. And for the third one, I'm going to do second cosine of 2. And I have an error in the domain. So once again, this does not exist. We could use the graphic organizer to check that out. For cosine, I cannot plug in 2. Even on a calculator, I can't plug in 2 for x and get a y value. It does not show up. It's not part of the domain. And I'm going to write that domain again so that we can see it. Okay. All right. Next up. Okay. I want to back up for 1 second just to look at those questions one more time. Even though these aren't points that we know, we can look at the graph and confirm that these answers make sense. So the first one was arctan of negative 8.45. I obviously don't have all the way to negative 8 on my x-axis, but imagine that it kept going this way to negative 8. The y value would be somewhere between here and this horizontal asymptote. So pretty close to negative pi over 2. And we did get an answer pretty close to negative pi over 2. If I type in negative pi over 2 on my calculator, I get negative 1.57. So I'm just a little bit above that. For the second one, we are on the sine inverse graph. I'm plugging in 0.2447, which so somewhere around here, and my answer is slightly positive, 0.2472. Makes sense? And we already looked at the third one. So just wanted to show you that these really are just points on those curves. But let's look at example 4. Use inverse properties. If possible, find the exact value of each. Okay, so in certain circumstances, these trig function inverses can cancel out and just leave you with the answer that's on the inside, right? Like if we take the square root of something squared, the square root and the squared can cancel out and leave you with the answer. That's not always the case, and I'm going to show you why. I'm going to actually illustrate this with that example that I just said. So let's say that we have the square root of 3 squared. Okay, well, 3 squared is 9, and the square root of 9 is 3. So it's as if the square root and the square just cancel out. But what if we had the square root of negative 3 squared written like this? Well, first you would square the negative 3, and you would get 9. The square root of 9 is positive 3. So even though the square root and the square are opposite operations, we didn't get quite the same answer. We got a variation of that answer, right? So that happens sometimes with the trig inverses as well. So we are going to keep track of that. This corresponds to the chart that's on the right of the front page. So composition of inverse trig functions. Remember, composition means like a function of another function. So if we have the proper domain of the original function inside, then this is telling us when things can actually cancel out. So for that first question, it was tangent of the arctangent of negative 5. So that's this one right here, tangent of arctangent. And this is telling us that we can plug in any x value from negative infinity to infinity in here, and it'll always be able to cancel out. So that's telling us that the tangent of the arctangent of negative 5 really does equal negative 5. And I can use a graphing calculator to confirm that if I wanted to. I could type in tangent of arctangent of negative 5, and I would get negative 5, right? Letter B. We have the arc sine of the sine of 5 pi over 3. So if we take a look at that chart from the first page and think about arc sine of sine. Arc sine of sine only works if the number I'm plugging in is between negative pi over 2 and pi over 2. 5 pi over 3 is definitely bigger than pi over 2. So this is going to not necessarily cross out. The reason that this interval is important because the arc sine will only give us answers between negative pi over 2 and pi over 2. So if the original angle is not between negative pi over 2 and pi over 2, there's no way we can get an answer between negative pi over 2 and pi over 2. But anyway, Let me show you how we actually solve a question like this. So we're just going to, little by little, kind of start on the inside and work our way out. So the sine of 5 pi over 3, we're just going to find that like normal using the unit circle. Since I have this graphic organizer out, I'm going to use this and think about where would I find the sine of 5 pi over 3. So I'm going to ignore these highlights, just look for 5 pi over 3, found it. The y value is the sine. So the initial answer is negative root 3 over 2. But now we're finding the arc sine of negative root 3 over 2. So now we're going to look at the sine inverse highlighting. Look for negative root 3 over 2. It's right here. So the answer is negative pi over 3. All right. So you can see my answer actually is in the same spot. It's coterminal to the original if you're thinking about the angle, but it's not exactly the same. I couldn't just cross those out. And you know what? It's not necessarily a bad idea to just consistently kind of track through the composition like we just did, if it's possible. Let's try letter C. Cosine of the cosine inverse of pi. So if I take a look at my composition rules on the front, cosine of cosine inverse will be allowed if the number I'm plugging in is between negative 1 and 1. Pi is 3.14, so that's not between negative 1 and 1, so that won't work. So let's start by finding the cosine inverse of pi. And if I take a look, I'm plugging in the number pi as the x value, which is green on my chart. And we've got a problem. That is outside the domain of cosine inverse. So that means that this actually does not exist. So we got to be careful. We cannot always cross out inverses of each other. We also sometimes find that they don't even exist. And that's because the domain, just like in the previous example, the domain of the cosine inverse of x is negative 1 to x to 1. And we were outside of that domain. All right, we got one more set of examples to get through. So let's take a look at example 5. Evaluating composition of functions. Find the exact value, no decimal, of each. So we first have the tangent of the arc cosine of 2/3. So this time, 2/3 is definitely not a number that shows up on our graphic organizer or our unit circle as something I can plug in for arc cosine. So that's not going to help. We also don't have like the cosine of an arc cosine. We have the tangent of an arc cosine. So when you see a question like this, it's actually going to take us back to thinking about x, y, and r. And let me tell you what I mean. I'm going to rewrite this question as another form of a question that means the same thing. And the question is, if cosine of some angle theta equals 2/3, we're going to find tangent of that angle. So arc cosine of 2/3 represents an angle, right? Whenever you have arc sine, arc cosine, arc tangent, the answer is an angle. That's why we shaded those in pink as the range, right? That's the output of that function, is these angles. So arc cosine of 2/3 is describing an angle. And we know because of the inverse properties that the cosine of that angle is 2/3. That's what the 2/3 means there. So if some angle has a cosine that happens to be 2/3, this larger statement is saying find the tangent of that angle. So what I'm saying here is we're breaking the composition of functions into its parts. So if cosine of some angle is 2/3, let's find the tangent of that described angle. And we can do that using x, y, and r. So I'm going to have cosine of theta equals 2/3. And I know that that is x over r. You might have to go back and look at that notes to remember that. But I'm going to need x, y, and r. So I'm going to make a chart here. And so x is going to be 2. R is going to be 3. And I need to find y. So I have x squared plus y squared equals r squared. So 2 squared plus y squared equals 3 squared. That's 4 plus y squared equals 9. Y squared equals 5. So y equals plus or minus root 5. And something that we did back when we learned about x, y, and r was that we always looked at what quadrant we were in so that we knew if x or y had to be positive or negative. In this specific context, when all we're given is some composition of functions, it's safe to say that the missing values are always going to be positive, and I'll show you why. This is going to be positive root 5. I'm going to write down here the note to always use the positive. All right, and on our graphic organizer, we were looking at arc cosine and finding the y value. Take a look. Any output or any angle that we're using here that's considered an answer from arc cosine, any of these pink angles have a y value that's positive, right? So the only choice for the y value in this context is for it to become positive. So we have to use the positive. All right, and then we were told to find tangent of that angle. So tangent is y over x. So we had a y of root 5 over an x of 2. And there's our answer. So we're going to do the same thing one more time for letter B. Cosine of arc sine of negative 3/5. Just to make this easier, I'm going to once again rewrite this as a question that we already know how to solve. If sine of theta equals negative 3/5, find cosine of theta. So let's try to do that work. So we have sine of theta equals negative 3/5, which I'm going to say is y over r. I'm going to list out x, y, and r. I know the y has to be the negative part because r is always positive. And I'm missing x, but I'm going to make it positive once I solve for it. So x squared plus y squared equals r squared. X squared plus negative 3 squared equals 5 squared. So x squared plus 9 equals 25. So x squared equals 25 minus 9, which is 16. So x is the square root of 16, which is 4. And like I said, we're going to make it positive. And that is because if you look at arc sine, we were missing the x value. All of the angles have ordered pairs that have positive x's. So that's how we know that x is positive in this situation. But again, you can just kind of assume that the missing value is always going to be positive in these cases. And so now we are going to need to find the cosine. So cosine is x over r, which in this case would be 4 over 5. All right. And that is the end of the notes. Thank you very much for watching, and have a great rest of the day.